So we all have our different ideas of what the mean means or what the mean is. I think that's good, but now let's actually define it, right? Let's actually give it a definition or a textbook definition. And for that, I want to talk a little bit about your grades. For example, I think in this class, I think homework is 20%, the project is 20%, the in-class problems are 20%, but the tests are actually 40%. Now, how do I calculate your final grade, right? Let's say you have a homework grade of 90 in total, like your total homework grade is 90 out of 100. Let's say that your project grade was, let's just give it a 75 out of 100. When I put together your in-class problems, then let's say that grade was 100. And let's say that the total grade for your exams are, let's say you add them up and get an average exam grade. On average, let's say you got like an 80 on your exams. And I know that homework is 20%, my project is 20%, my in-class problems are 20%, but my tests are actually 40%. How do you know your final grade? I hope this will be helpful for all of you, because I'm not going to give you your final grade until the very end, right? So how can you figure out your final grade ahead of time? So you multiply each by their weight, and then you add them together. Good. And that's absolutely right? So you get 90%, but 90% is actually only 20% of the final grade. So I would actually take 90% and then multiply it by 90, sorry, and multiply it by 20%. I will have my 75 and multiply it by 20%. I will have my 100 and multiply it by 20%, and I will have my 80, but that 80 I would actually multiply it by 40%, which means that the exams have a higher weight than everything else. And of course, my final grade is just all of these added up, because if you were to have 100 for all of these, and then you run this calculation, your final answer is 100. You get 20 plus 20 plus 20 plus 40, that's 100. But if you don't, then you do this, and then you're going to get your final grade. I don't know what that final grade is. You can figure it out if you want. But essentially, that is what we're doing, right? Your final grade, according to Bailey, is 85. So what we're doing here is essentially we're calculating a mean. Like, we just calculated the mean of your grade, and that is your final grade in class, the mean of your grade on all of the other assignments. All we're doing here is we're multiplying each of these outcomes with their percentage, or in this case, how much of the entire grade distribution do they contribute to, right? What we're doing here is the same thing. We're taking each outcome and then we're multiplying it by their probabilities, which is essentially how much of the probability distributions do they contribute to. So a mean, which we're gonna write down with the Greek letter mi, or if you speak fraternity Greek, it'll be mu, but yeah, the Greek letter mi. Sometimes we write the mean as a function capital E of x, because the mean is taken for the entire random variable, is essentially the sum, right, of each outcome, 90, 75, 180, times its probability. That is what the mean is, the sum of each outcome times its probability. Let's say you have n outcomes, so this would be from I equals 1 to n, and that's a little bit of a more formal definition of the mean, the sum of the product of each outcome and its probability. That's the first measure we're going to learn, and one of the most important measures we want to use for studying data. So what does the mean? Essentially, it is a measure of the center of a probability distribution. It doesn't really give me the middle value, but if I were to plot that probability distribution, the mean would essentially be a number that tends towards the center. Sometimes we call it expected value, which is why this E occurs, because essentially my distribution would feel like if my values are kind of tending towards that center. It's like they want to go towards that center. So that's why we call it a mean, or we also call it the expected value, which is where this E function comes from. Notice that E is a function of capital X because the mean is taken for the entire variable, not for individual outcomes, right? You have to include all of the outcomes here. You add up all of the outcomes, so it's actually a function of the entire variable, not of individual outcomes. Now, don't feel bad. Everything else you said about how you would calculate or what you think is the mean actually is, they are all very important measures, which we're going to learn later. So when we talked about just the arithmetic average and the mode and the median, all of those are very important measures, and we will learn about those in the future. But for now, when I talk about the mean actually takes into account the probability or the weight of each outcome in the probability distribution. Now, the mean is not really enough to tell us or to properly describe a probability distribution. Sometimes the mean is the end goal, such as in the case of a final grade or a GPA. It's like that's what you care about because that's the end goal. But other times you need to consider other aspects of a probability distribution. And one of the most important aspects after the mean would be the dispersion. In other words, how close or how far away are most of my values going to be from that mean? Because you may have a case where your mean and all of your values are very, very close to each other. But you may have other cases where your values are dispersed. And that dispersion is important. In fact, it's very important in statistics, because statistics is not just about finding values. It's about figuring out trends and figuring out possible outcomes. And the bigger the dispersion, right, the more possible outcomes you have, the harder it is to actually study something, right? If everything tends towards one value, but it's actually very, very dispersed, then you can't certainly, with certainty, say my value will be this, my value will be that. So that measure of dispersion is what we call the variance. In fact, we call it variance because it's a measure of the variability of a probability distribution. It's also the expected squared deviation of a variable from its mean. In other words, if I take the deviation of a random variable and all the outcomes in it, if I figure out how it deviates from the mean, how far away it is from the mean, and then I square that value, then I am getting my variance. Now, variance is typically written as sigma squared, and you'll learn why this square is necessary. That's the error bars on an Excel graph right. I'm not really sure which type of graph you are referring to, so I don't want to answer that question and then be incorrect. But definitely, you'll figure that out, I guess, when we're doing descriptive statistics, like a scatter plot. Yeah, exactly. Yeah. Well, yes and no. So variance is actually the square of that dispersion, okay, the square. And we'll understand why we need a square when we actually see the equation for variance. So we express this as sigma squared. Again, the square is very important, or sometimes as the function v. And here, v is for variance. Just like with the mean, you take that function over the entire variable. And that function can be found, okay, as the sum of the difference between my individual outcome and the mean of my random variable. But then we have to square it. That's where this square comes from. And of course, we need to weigh each outcome because different outcomes will have different probabilities of appearing. But we need to weigh each outcome to its probability mass function. So that is my variance. It gives me the square of the dispersion of my values. Now, why do you think that square is necessary? Why is it necessary to square these values? Any ideas? So what happens if you don't square it? For example, I just take any value, subtract the mean from that value. Exactly, Bailey is absolutely right. To eliminate negative numbers, right? Because if you have values that are smaller than the mean, but then you're subtracting the mean, you get negative values, right? And in that case, when you add them up, you'll get positives plus negatives. You're gonna get a number really, really close to zero. And then you actually are not measuring the dispersion. So that's why it's important to square these values, because it helps us get rid of negative values. Now, of course, we mentioned that this is the square of the dispersion. Is there such a thing as a dispersion? Why not just absolute value? Well, first of all, absolute value is a function. So it's not very helpful here, because if we take a difference and the probability of that difference, then we're not exactly measuring the dispersion. And you'll see when we look at another variable called standard deviation, you'll see that it's actually not quite the same thing. Okay, so it is definitely necessary to square those values. Taking the absolute value is not very helpful. It's not going to be very helpful here. And you'll see why when we define the standard deviation. So we mentioned that the variance is the square of that dispersion. But then the dispersion itself is what we call the standard deviation. Now, the standard deviation is identified as a sigma. Of course, if it's identified as a sigma, and sometimes we call it a function SD, then all it is just the square root of the variance. Now, if you actually look at this, you may realize, right, that your standard deviation is not the same as taking the absolute value here, because you're actually squaring the entire thing, the sum of the entire thing, not squaring the individual values. And that is actually what gives us a measure of dispersion of our data. If we were to use absolute value, we would not get the dispersion of our data. But if we find the variance and then square that term to take the standard deviation, then we do. Now, all of these become a little bit more fun when we talk about descriptive statistics, just because we can actually see them in action. But right now, what I would want you to think of is that the mean is where all the values are trying to concentrate into. And the standard deviation is how far away are those values, are the bulk of the values from that mean. So in the chat we have, so variance is sigma squared and SD is just sigma in terms of notation. Yes, correct. Yeah, and the sigma squared and the sigma is just there to tell you that sigma is just the square root of sigma squared positive, by the way. Or so if we find the variance, all we have to do is take the square root to get the standard deviation. You'll see on the notes that there's a special form of variance. Now, this special form was more helpful before we had computers, because calculating this by hand when you're dealing with thousands of data points is not very helpful. But we can derive this nice little special form of the variance, which gives us the sum, okay, of each outcome squared times the probability of that outcome. And remember, this is from I equals 1 to n, minus the mean squared. And you'll see that this is actually just the mean. I'll just call it function e, the mean of x squared minus the mean of x squared. Because all we're doing here is we're taking a value called x squared, and then we're finding the mean of that value. Remember, this is just a variable. This can be x, this can be y, this can be anything, but it's a random variable. So I can create a random variable called x squared, which is just my outcomes squared. And then if I weigh them against the probability distribution, then I get the mean. We're not actually going to spend too much time deriving this, or any time at all deriving this. I used to do this. We had a class, a data collection class, where we would just sit down and derive this. The way you land at this is by taking this expression and expanding it, right? You take x minus mu times x minus mu because it's squared, and you do all your little math, and you're going to end up with this value. But that usually takes up a lot of our time, and I find it fun because I love doing these little things, these little like math things, like going, oh, let's see what multiplying this gives me. But I noticed that most students saw that as a bit of a waste of time, because nowadays, in the age of computers and spreadsheets, this is the easiest way. This is an easy way of calculating the variance, right? That we don't need this because we can actually calculate everything with spreadsheets. However, I don't want to deprive you of all that fun, so I did make this part 3 of the project, which is due later, not on Monday. So you'll still see it. You'll still be able to figure that, to use it, but just not today. Okay. Anyway, those are the three measures, the three important measures that we want to talk about today: the mean, the variance, and the standard deviation. Moving forward in this class, whenever I give you a data set, by default, you should already think of what is the mean, what is the variance, what is the standard deviation, so that you can analyze your data set, right? If you look at a probability distribution, right? Even before I ask you, right? Just by default, you want to know what the mean is, you want to know what the variance is, and you want to know what the standard deviation is. We're going to do a very quick example from the textbook. And I would recommend, instead of trying to solve this example by hand, I would recommend that you actually try to follow up on your spreadsheets. And the reason I want to recommend this is because, again, it's going to be important to know how to solve this in a spreadsheet. There are functions for all of these, for variance, for standard deviation, for mean. There are functions in Excel that just give you the value directly. But I would say you would get a lot more out of this class if you actually learn how to calculate using the equations. Still using the spreadsheet, but instead of using the built-in functions, actually write down the equations first so that you actually understand what's going on. And then you can actually see the different steps into calculating something, okay? So let's look at a quick example from the textbook. And in this example, we are simply going to calculate the three measures that we've already covered of a probability distribution. Now remember, I don't really have to tell you, give me the mean, give me the variance, give me the standard deviation. That's something that by default you want to calculate, because it will definitely help you interpret and understand your data sets, okay? All right, let's just take the data, right, from our camera flash example. And if we remember correctly, we had that our random variable x had values of 0, 1, 2, 3, and then probability mass functions of 0.008, 0.096, 0.384, and 0.512. Okay. Now, what I would like to do for this data is, you have your probability distribution. I'd like to know what is the expected value of tests a camera flash will pass. In other words, I'm not saying how, what's the probability that a camera will pass 2 or 3. No. I'm saying if you were to take that camera flash and then test it at any point in time, right, or at a point in time, how many tests would that camera flash be expected to pass? When I'm asking about an expected value, a value that you're hoping to look at, that you think your data is going to tend towards, what measure am I talking about? When I say, what is the expected number of tests a camera flash will pass? The mean. Yeah, that's correct. Remember, the mean is the expected value. So when I tell you how many tests is this camera flash expected to pass, I'm asking for the mean of your probability distribution. And it's very important that you understand that, right? That when I say expected, what I'm talking about, right, is the mean. So let's find that mean. You may recall, right, from a few minutes ago, that the mean is simply the sum of the product of each outcome times its probability. So if you are using Excel, it may be helpful to create a column that gives you, right, the product of each outcome times its probability mass function. And that should allow us to calculate the mean. So for each outcome, all we're doing is we're multiplying the outcome times its probability. Therefore, my first value will be what? 0. Good. My second value? My second value? Yeah, 0.096. I'm asking these values on purpose, right? I'm not looking for math whizzes here. These are pretty simple to find. All right. You can do the rest yourselves, and just so you have the answers, my third value will be 0.768. My fourth value will be 1.536. Now this is just outcome times probability, but what the mean is, remember, actually the sum of outcome times probability. So if you add all of these values up, I actually get a mean of about 2.4. Now, what does that mean, right? What does that mean? What does that mean? What it means is that if I were to test a camera flash at random for this type of camera, it is expected to pass 2.4 tests. Now, you may think, wait a minute, what does it mean to pass 2.4 tests? I mean, we already said that's a discrete random variable. There is no such thing as 2.4, but when I say that you're expected to pass 2.4 tests, that means, right, that between passing 2 tests and passing 3 tests, the camera is more likely to pass 2 tests, right? Just because 2.4 is closer to 2, right? So that is my mean, right? That is my mean, and that actually gives me an outlook that's a little bit different, right, from what you see by just looking at the probability distribution on its own. Like having 2.5 kids. Yeah, that's right. If you hear something about how the average family has 2.5 kids, like what does it mean to have 2.5 kids? Unless you're into like, you know, like weird stuff, right? What is 2.5 kids? It's just, that just means that on average, right, the value, the number of kids a family has tends towards that number. Now, one thing we want to realize, just because the mean is the center of the probability distribution, in other words, my values tend towards that value, that doesn't mean that the mean has to be one of the possible outcomes. In fact, we can see from here that the mean is actually not one of these outcomes. So my outcomes are tending towards 2.4. They seem to want to go towards 2.4, but none of them are actually 2.4. So that is the mean. And hopefully we understand that, right? That the mean doesn't have to be an actual value, an actual outcome, but still values can still tend towards that outcome. Sometimes when we are talking about test grades, you may see, well, the average grade was 75, but that doesn't mean that students got 75. It could mean that some students had more than 75, some students had less than 75, but then if you take their weights, right, then it seems like the grades are trying to go at 75. One way to visualize the mean a little bit more from a mechanical perspective, you being engineers, is kind of like a centroid, right? You think of a centroid, is that like an asymptote? Your data is tending towards a number? I wouldn't call it an asymptote, to be honest, because an asymptote, what that tells me is that my numbers are trying to reach there and will get as close as possible without reaching. In the case of discrete random variables, they don't necessarily have to get as close as possible, right? An asymptote, you get basically close, you know, infinitely close to that number. That's happened with discrete random variables. Instead of using that term, I would prefer to look at the mean as a centroid. You think of the centroid, right, as that point where you can perfectly balance anything, right? You can perfectly balance any object if you are balancing it by its centroid, because at the centroid, you have equal distributions of that volume, or if it's a center of gravity, then equal distributions of the weight, right, in every single direction. And that's what the mean is. If I were to take this data set and then graph it and then try to balance it, at 2.4, I would have equal distribution of all my probabilities and outcomes in both directions, which means that from this mean, about 50% of your outcomes lie to the left of this mean, or the likelihood of 50% lies to the left of your mean, and then the likelihood of 50% lies to the right of your mean. So that is what the mean essentially represents. Now I could say, right, I could say, give me the deviation, right, from the mean. In other words, how dispersed are these data from the mean? Now, when I'm asking for deviation or dispersion, what exactly am I looking for? Am I looking for variance or standard deviation? I should have used a different word. When I'm asking for dispersion, what exactly am I looking for? Yeah, yes and no, right? It's like it is the variance, but remember the variance is squared, right? So if I don't say give me the square of the dispersion, if I just say give me the dispersion, really I'm looking for standard deviation. Now, don't worry, I'm not gonna be as vague in the test where I'm like, forcing you to tell me if I'm looking for sigma or sigma squared. But just keep in mind that the deviation is the standard deviation, the dispersion is standard deviation, and variance is actually, it's a measure of it, but it gives me the square of it, not really the thing itself. So just to keep that in mind, we do want standard deviation, but of course, this is kind of a way of me to cheat, right? Ask you to calculate two things, even though it's, I'm asking for one, you still have to calculate both. To get the standard deviation, you still have to give me the variance. So regardless, Renee is correct, right? You still have to find the variance because you need to give me the variance in order to determine the standard deviation. So how do we determine the variance? You may recall from the equation that variance is just the difference between each value and the mean squared times the probability of that outcome. And that is exactly what we can find. We can find, right, in this case, each outcome minus the mean, square it, and then multiply it times the probability of said outcome. And I hope that you're doing this in Excel. It'll be a lot faster if you do. All we're doing here is we're taking this value minus this value, square that, and then multiply by this value. For the next cell, we're taking this value minus this value, square it, and multiply by this value. If we do this for all cells, then we're going to get the following values. And again, if you're doing it in Excel, once you get the first formula in, all you have to do is drag down your formulas so that you can calculate for everything. Now, of course, this is just x minus mu squared times the probability mass function. Oh, you could be correct, right? I just calculated these on the fly. So can somebody confirm which value is correct? And remember, this is 0.096, right? And so it's 1 minus 2.4, right? So that's negative 1.4. You square it, and then you multiply by 0.096. Somebody confirm which values are correct. Oh, for 2 and 3. So this will be 2 minus 2.4, so that's negative 0.4. You square that, negative 0.4 squared is negative, sorry, it's just 0.16, and then you multiply by 0.384. So 0.384 times 0.16. Okay, so Marco, you may want to check your calculations. There may be something a little bit wrong there. So just make sure you double check. But same applies to everyone. Don't assume that everything I'm giving you is correct. Even today, we found a small error on the notes. So just don't assume that everything I'm giving you is correct. Always calculate it yourselves and all that stuff. So if we add up all these values, we get our standard deviation. And again, in Excel, that's just as easy as just writing down equals sum and select all these cells. And that's it. So for this case, we get a standard deviation of about 0.48. But that's not what I asked for, right? I asked for the dispersion, right? I keep saying something. We get a variance of about 4.48. Let me just write it down so I don't keep messing up the words. We get a variance of about 0.48, but that's not what I asked for, right? I asked for a dispersion, or I asked for a deviation. So how do we take this number and turn it into a deviation? We have 0.48. How do we turn it into a deviation? Yeah, we take the square root. That's all we do, right? We take the square root. So in this case, my standard deviation is just the square root of sigma squared. And the square root of 0.48 is roughly 0.693. Roughly. And that's it. I looked at the data set. I asked for expected value. I asked for the dispersion. And really, that's just jargon, right? All I'm asking really is, what's the mean, what's the standard deviation? You hear expected value, dispersion, really, what's the mean, what's the standard deviation? Standard deviation is the value that we typically want, is the measure that is most used. But in this class, because you always need to calculate the variance, and you'll see that the examples ask you to calculate the variance first, just because it's necessary. But really standard deviation is the value that you're gonna want to use. Yeah, so Marco, just double check your work, make sure everything's correct. Remember, this is 2.4, this is 2, this is 0.384. Hopefully you can get the correct number. But if not, I think some other students got my numbers, so I'm assuming my numbers are correct. But that's something you want to always keep an eye out on, especially for the test, right? Because you want to make sure that you get the correct answers for the test. It makes it easier for me to grade, okay? So those are the three measures that I wanted to talk about. Now, I'd like to use the remainder of this class to talk about some common probability distributions. Not all probability distributions are the same, right? This one has these values. Other probability distributions will have other values. So there will be different types of probability distributions, but sometimes your probability distribution can be kind of grouped together because of similar features. And I'd like to introduce a couple of probability distributions. If we can figure this out ahead of time, I may be able to talk about two different probability distributions, the uniform distribution and the binomial distribution. But let's just try our best to go through them and make sure that we understand all of these, okay? Let's start with a uniform probability distribution. And just to make it a little bit more specific, let's say we're looking for a discrete uniform probability distribution. Keyword here is discrete because that means that our outcomes can be counted. In other words, I can say there are n outcomes, for example. But uniform, all that uniform means is that if I were to plot it, it would be a straight line, right? It means that the probability in each value doesn't change. It's uniform, right? It does not change. Now, if the probability for each value, for each outcome in my random variable is uniform, then what this is telling me is that my outcomes are equally likely to occur. So if my outcomes are equally likely to occur, then I actually have a very easy way of finding my probability mass function. We've already talked about this in the previous class, right? We said that for equally likely outcomes, the probability was simply a function of the number of outcomes. Does anybody remember what was that probability? And if you don't remember, you don't recall, think of flipping a coin, right? And how we get that probability of 50-50. Let's say for n outcomes. What is the probability of each outcome if they are uniform? So it's the same outcome, equally likely outcomes. Yeah, that's correct, 1 over n. And that's all it is, right? For a random variable that has n outcomes, my probability distribution is simply 1 over n. Now, this is special. And the reason this is special is because if I were to calculate the mean, for example, the mean is x times f of x. But f of x is a constant. It's just 1 over n. Because it's a constant, it's almost like if we can take it out of the sum, right? So my mean ends up becoming just the sum of x divided by n. And that's the average that some of you were already talking about, right? They were saying add up everything and divide it by the number of items. That is the mean of a uniform distribution, when you add everything up and divide it by n. So for a discrete uniform distribution, my mean is going to be equal to the sum of all my outcomes divided by the number of outcomes. Similarly, my standard deviation, right, is going to be equal to the sum of my outcomes minus the mean squared. And because you multiply by the probability distribution, but that's constant for every outcome, then it's just all this divided by n. This is a very interesting distribution because it's very easy to quantify. And notice that it highly depends on the number of outcomes. In other words, for discrete uniform distribution, your number of outcomes is really what governs what governs your mean and your standard deviation. Now, this is actually a very, very easy to study distribution. There are some special cases of this uniform distribution where you can calculate the mean and the variance using simplified formulas. Okay. Now, I don't want to go through all of these special cases. One, for example, is what if my discrete uniform distribution has consecutive integers? So let's say 3, 4, 5, 6, 7. Then in that case, these equations actually simplify a little bit. Or we could say, what if it, instead of 3, 4, 5, 6, 7, what if it's 8, 9, 10, 11, 12, 13, 14, right? As long as the outcomes are consecutive integers, then my mean and my standard deviation can be calculated with special formulas. Now, that's actually not something that I feel it's worth covering because it's it's just running a simplification, and when you calculate it, then you get a nice, easier to memorize formula. But you do have it on your book on section 3.4. So if you do want to do a little bit of independent study, I would recommend that you read section 3.4. And there are 3 good examples, 310, 311, and 312. I think those are good examples that kind of force you to practice with different special cases of discrete uniform distributions. I personally don't think it's necessary to cover them in this course because very, very few of the distributions we'll see are discrete and uniform. We're going to focus on a little bit more realistic distributions. But I do think that would be it would be very good for you to self-study these cases, because who knows, maybe if you run into one of them, the simplified forms maybe will help you calculate things in a smaller amount of time. But even if you don't know all these special cases, actually you don't have to, because as long as you know that it's discrete and uniform, these equations will apply to any discrete uniform distribution. So special cases are just ways to simplify your work. But even if you don't know them, you can still apply these and get the same correct results. So that is a discrete uniform distribution. I'd like to talk about another type of distribution, but this one, I think this one warrants a little bit more introduction. Okay. So the first thing I would like to talk about is a definition. And so, it's important to define some things so that we're all using the same jargon, we're all using the same words. I would like to define a Bernoulli trial. Now, first off, what is a trial? Well, let's figure out what Bernoulli is. So Bernoulli, if you've taken a fluid mechanics class, then you've heard the name Bernoulli before. This is actually not the same Bernoulli. The Bernoullis were a family of prominent mathematicians, right? Jacob Bernoulli, Daniel Bernoulli, Johann Bernoulli, and others, many, many others. The fluid mechanics Bernoulli is Daniel Bernoulli, but here, this trial is actually, the Bernoulli trial is actually named after Jacob Bernoulli. Now, Jacob Bernoulli, as you know, was a mathematician and a prominent member of that prominent family. And Bernoulli developed a process that nowadays is called the Bernoulli process. And the Bernoulli process is a sequence of binary random variables which have consistent probability distributions. Now that's a mouthful, I know. So let me just write down the definition first, and then we'll look at each part of the definition and then define any additional terms as necessary. So my Bernoulli process is a sequence of binary random variables with consistent probability distributions. Okay, but we got to define what every single word in that sentence means. So first off, let's talk about what a binary random variable would be. So what do you think a binary, and you can look at the name and kind of tell me, what do you think a binary random variable is? Yeah, two outcomes, right? Binary means two, right? It comes from two. So there's only two outcomes. So a Bernoulli process is a sequence of these random variables, each of which only has two outcomes. And a binary random variable will actually be will play a very key role here in understanding some of these probability distributions. Now, those outcomes can be whatever you want them to be, but because they are only two outcomes, then we typically define those outcomes as success or failure. You can call them yes or no, 0 and 1, X and O. But essentially, it's helpful for us to identify the outcomes as what we're looking for and everything else. So success or failure. It's very, very important to understand our outcomes as that, success or failure. Success is whatever you want it to be, right? And then failure is just everything else. For example, if we're flipping a coin, can they be true or false? Yes, true or false. Like I said, whatever you want, true or false, 0 or 1, success or failure. The important thing is that one of those values is the one that we are hoping for, and the other one is everything else. So if you're flipping a coin and you want to land on heads, then by your standards, success would be landing on heads and failure would be everything else, which is landing on tails. So coin flip is a binary variable with two outcomes, heads and tails. But for the purposes of the Bernoulli process, we're going to identify one of those outcomes as a success and the other outcome as failures. Now, these outcomes are typically numbered as 0 and 1. And we typically say that number 1 would be success and 0 would be failure. And again, this allows us to see how close we are to success or how close we are to failure. Bailey gives us a very interesting point, right? We could say that rolling a die could be the same thing, where success is 1, let's say, and failure is 2 to 6. So let's say you're rolling a die, you're maybe casting lots like in biblical times or placing a bet, and you want to land at 1. Let's say you're trying to land at the lowest possible number, at just 1. Then you could catalog success as landing at 1 and failure as everything else. And that gives you a binary variable. Notice that we took a non-binary random variable. I sound like a liberal here. Notice that we took a non-binary random variable and then we turned it into a binary variable. No one wants a net 1. I don't understand, but okay. So essentially, success is what we're looking for. Oh, Dungeons and Dragons jokes, sorry. Nerd. So essentially what we are looking for, right, is success and or failure, right? Some students are recommending -1 point for the Dungeons and Dragons joke. I will consider that. Yes, I will consider that. Success is what you want it to be, failure is everything else. Okay, we gotta get back to the class before I get too distracted here. Here, we are going to say that the probability of success is P, okay? So the probability of success is P. Let's do Bailey's example with rolling a die. You're rolling a die, and let's say that each number is equally likely to occur. So you have 6 numbers. The probability of each number is 1/6. But for you, success is just 1, and then failure is 2 to 6. For that example, what would be the probability of success? It's a binary variable where the probability of success is 1/6. Good. And if that's the case, then what is the probability of failure? Yep, 5/6. That's correct. Is there a way to generalize that so that we can write down my probability of failure as a function of P? One minus P, correct. You know that because it's only two variables, if you add them up, the probabilities have to add up to 1. So if success is P, that means failure will be 1 minus P. Good, that's absolutely right. I already talked about flipping a coin. Some other examples, remember this can apply to everything. I think Bailey's turning this into a rolling a die example is brilliant because it's something that's wasn't binary and then you turn it binary. But other things are asking yes or no questions in a survey, right? Do you agree with this, yes or no, right? It's one can be success, one can be failure, but the idea is two outcomes. You want to test if a computer screen works, right? Does it work or does it not work? Those are two outcomes. You can observe a car drive through a highway without incident, right? Without crashing or a fender bender or anything, right? So it's like either there was no incident or there was an incident. Perhaps, perhaps in my case, success would be no incident, right? I don't want to have an incident. I don't want to have an accident. So for me, that would be success. But it is what you want it to be. Now, a Bernoulli trial, because that's really what we're going to talk about. A Bernoulli trial is that binary random variable, right? That forms that Bernoulli process. Now, we say that the Bernoulli trials are going to be independent of each other. For example, if you're flipping a coin, and let's say the coin is perfectly balanced, then the probability of landing heads or tails is always going to be 50% each. It doesn't matter how many times you flip the coin, it's always going to be 50%, right? You flip it, 50%. If you're gonna flip it again, for that second run, it's also 50%. If you're gonna flip it again, for that third run, it's also 50%. So consider our coin flips as Bernoulli trials, then we can say that each coin flip is independent of the previous and the next coin flip, in that they will have exactly the same probability distribution. They're not going to affect each other, okay? So that means that P and 1 minus P are going to be constant throughout the entire experiment, right? Which we call a Bernoulli process, okay? I wanted to define those because I'm going to be using these terms to talk about the next distribution, right? Which is a binomial distribution. So why do I have to define Bernoulli trials? Because you see, a binomial distribution will consist of Bernoulli trials. So if we can take a Bernoulli trial, and you already know that a Bernoulli trial is just going to be one where there's only two outcomes, right? You can repeat the experiment as many times as you want, but they're not independent, but they are independent of each other, and the probabilities remain constant throughout the experiment. Now, if you take an experiment where your experiment will consist of, let's say, n Bernoulli trials. Okay, so n Bernoulli trials. It can be 10, it can be 20, whatever you want. Okay? Then we can say, right, that a random variable for that experiment could be, right, a binomial random variable, a variable that gives me the outcome of that experiment. Now here, this is something important. I remember back in maybe the first day or the second day of class, one of your classmates asked, how does the probability change the more you do something, the more you run an experiment, the more you repeat it? Now, what we're learning here from the Bernoulli trial is that each trial is independent of the one before it. However, just because each trial is independent of the one before it doesn't mean that if we take the experiment as a whole, our distributions will always be the same. In fact, what the binomial distribution is going to tell us is that depending on the number of times you run the trials, the number of times you run the experiment, then your probability mass function will change. It will vary. So a binomial distribution will have a probability mass function, and you'll see that that probability mass function is not going to be a constant. It's not going to be p and 1 minus p, such as in a Bernoulli trial. Since your experiment consists of running n Bernoulli trials, then your trial is actually going to be, your probability is actually going to be a function of the number of trials plus which trial you are at one point in time. Now that distribution is an interesting distribution. It consists of the binomial coefficient. You may recall this from the second day of classes, times the probability of success elevated to the power of x, where x is the current trial, right? Times the probability of failure elevated to the power of n minus x. So this is the remaining trials. Now you may recall this is the binomial coefficient, which was n choose x. You may remember this. This was n choose x, which is a set of factorials, which you already have on your notes. But what this is telling me, okay, is that you can actually determine that your distribution is going to depend, right, on the number of times you plan to run the experiment and what run you are at the moment. Now this is interesting because what we say above is that these are independent. At each individual trial, the probabilities don't change. But once again, here at the binomial distribution, we're not really looking at individual trials now. We're actually looking at the experiment as a whole, the collection of trials as a whole. So you can use this binomial distribution's probability mass function, right, to determine, right, to determine the probability distribution, right? And you'll see that as long as you have value for p and you have value for n, then you can tabulate values for different x's, right, from 1 all the way to n. And you'll have your little probability distribution, and if you want to graph it, that's fine, but that will be your binomial distribution. I want to shy away from graphing yet. One, because I'm not actually the best at drawing things to scale. And two, because as much as I would like you to visualize everything, and we will get to a week where it'll be dedicated to visualizing things, I do want you to kind of like take in the math first. Make sure you know how to use it. Visualizing things is definitely going to help us when it comes to talking about means and variances, but it can also lead to some misinterpretations of data if not done properly. And I am just not the person to teach you how to do it properly, which is that I would prefer to actually cover these a little bit first, use them, understand them, and then visualize them, okay? That's the disadvantages of being taught statistics by someone who is not a statistician. But I mean, that is the world we're living in right now, okay? So that is my binomial distribution. And you can take this and calculate the mean and the variance. Remember, mean is just fx times f of x, right? You take all this, you multiply by x, and then you add them up. Now you'll notice that if you do that, you're going to find special or simplified cases, simplified formulas for your mean, your variance, and your standard deviation. Now, I'm not really looking towards deriving them right now, but just to give you an example of what that would look like, the mean of a binomial distribution is actually very easy. It's actually just going to be n times p, which means that the mean, just like with other types of, just like with, with uniform distributions, the mean is actually a function of the number of times you run the experiment. And I want to see what this is telling me. You can see that the mean is the expected value, right? And we're saying that the expected value is the number of times I run the experiment times the probability of success, right? And it's really interesting because you'll notice that the more times you run the experiment, right, the more it's going to try to trend towards this, right, towards the probability of success. But again, that's a little bit better if you just derive the equation and see it on your own. The standard deviation, the variance, my bad, is just going to be NP times 1 minus P. So once again, the number of times you run the experiment times the probability of success times the probability of failure. If you're interested in seeing all the math behind, I know this is not a math class, but I also don't like just giving out equations, you know, and then calling it a day. But if you are interested in seeing all the math behind this, you can check out section 3.5 from your book. And there are 4 examples, 313, 314, 315, and 316, that kind of show you how to use a binomial distribution. Now, we will work on examples, but I don't want to really spend much of our class in just plug and chug examples. I prefer to dedicate our class after we learn a little bit more about different types of distributions. I prefer to just do cases and then have you try to figure out what the distribution is. I do think we learn a little bit more about that, but you can do the examples from the book and follow them along. They have the solutions written. I think it'll be good for you to practice those before we start to work on more complicated examples. If you choose not to, that's also fine. But you know, it's always good practice to try some examples, and you'll definitely get some practice on the homework anyway. So why do we call this the binomial distribution? Well, because it uses the binomial coefficient. And last time we talked about the binomial coefficient, right? N choose X in this case, or N choose K, or N choose R. And I mentioned that, you know, this does come, there's a reason for this. This comes from something. There's a reason why it's called the binomial coefficient, but we weren't going to talk about it yet. Now, I actually think we have enough time in this class to, you know, talk a little bit about the binomial coefficient. So the reason the binomial coefficient receives its name is because it is the coefficient found in the binomial expansion. So it's just a quick math review, kind of like a little parentheses in this class. Now, if you're not familiar with the binomial expansion, if you haven't done really series and stuff, it's okay. Essentially, if we take 2 constants, a and b, then the binomial expansion tells me that I can find a plus b elevated to the power of n by simply adding up, right, n choose k, a to the power of k, and b to the power of n minus k. And this is from from k equals 0 all the way to n. Because this is the coefficient, right? It's n factorial over k factorial times n minus k factorial. Then we call it the binomial coefficient. Now, why do I want to do this? Do I want you to learn all this math and all the theory behind? I mean, I don't particularly care too much, although I think you should. Whether or not you do is up to you. But the reason I want to do this is because the binomial expansion it's very interesting, right? I'd like for you to look at your binomial distribution and look at my binomial expansion and tell me what you see. Like what does this tell you? Do you notice anything? Do you notice any patterns? Do you notice any trends? Maybe any similarities, any differences between the binomial distribution and the binomial expansion? Any ideas? So Christian says it looks like the equation. It does, right? They do look somewhat similar. Like the probability mass function looks kind of similar here. I mean, are there any values we can give to A and B so that this looks like my probability mass function for a binomial distribution? Could you say that A equals P and then B equals, I see P minus 1, I think you mean 1 minus P. Yeah, That's absolutely right. And let's do that. Let's do that and see where we end up. So if A here equals P and B equals 1 minus P, then we see that this equation will become, let's see, P, or in this case, N, choose K, P to the power of K, 1 minus P to the power of N minus K. And this is from K equals 0 to N. Now, remember, what's this saying? Well, here K is my variable, right? So this can be actually my random variable. In fact, I don't even have to call it K. I could just call it X, right? So this would be N choose X. This should be P to the X, because it's just a variable, something that changes, something that varies. Now, what is this? Well, this is my probability mass function, right? In other words, this part inside the sum is f of x. So what I'm doing here is I'm adding up f of x for all of my x's. And if I add up all of the probabilities in my random variable, what should that equal to? If I add up all of my probabilities, all of my probability mass functions, it should equal to 1, right? It should. Now, here's the question. If A equals P and B equals 1 minus P, what does the left side of the equation become? Let's see. A equals P and B equals 1 minus P. What does the left side of the equation become? One. That's absolutely right, right? 1. 1 to the power of anything is 1, right? So that's absolutely right, right? This is just 1. And this is very, very important, right? Because what we are seeing here, right, is that the binomial expansion satisfies the binomial distribution, right? It makes sense mathematically, right? Because mathematically we know that a plus b to the power of n is equal to this, and because that is a, you know, that's just how it works, that is math, then the binomial distribution should satisfy it, and it does, right? It does. From a statistical point of view, it does, because it tells me that the sum of this probability mass function is to equal to 1. So that is where the binomial distribution comes from. Again, we're going to look at these maybe not in as much detail as some of the other distributions. So this is more of a basic introduction to some of your probability, some of the common probability distributions, but there are others that are a little bit more common that we may want to turn our attention more towards. Of course, I still think you should try to do the examples in the book just to get some feel and practice, but we will do a little bit more some more complex examples in the class in order to actually get more familiarized with our probability distributions. Now, before we end today's class, I do want to make a recommendation, right? Obviously, it's a recommendation, and I'm not asking you to do this for a grade, but just as a way to help you with your studies, I found that it's actually very helpful to have a little table handy, because we're going to be looking at a lot of different probability distributions, and sometimes you don't want to have to calculate the mean and the standard deviation for every single one, right? Sometimes it may be better to just tabulate your values, okay? So that once you know what probability distribution we are looking at, you can easily look up the probability mass function, you can look up the mean, the variance, and of course, by extension, the standard deviation. I'm going to show you what that table looks like. It's here, and you have it on your notes as well. So this is my recommendation of a table you may want to prepare. And I've actually already pre-filled this table with the distributions we have seen. So we know that a discrete random variable is going to have a probability mass function, which is just f of x. That's just a definition. And we know that the general definition of a mean is just the sum of x times its probability mass function. And the general definition of a standard deviation is x minus mu squared times f of x. Uh, Tajiri asks, is this document on D2L? Well, if you're asking me that, I'm assuming that you haven't really looked at the documents that I've uploaded on D2L. So obviously the answer is yes, but I would recommend that you look at the materials I'm uploading before coming, maybe before coming to class, or at least just browse them a little bit. But yeah, it is. You can find it there. All right. Of course, this table is not like all, like, you know, it doesn't include everything, right? But I've tried to pre-fill it out just a little bit with some of the ones we've talked about today. So this is just a general definition of discrete. But we know that for a discrete uniform distribution, we already said that the probability mass function is 1 over n, and then the mean is just sum of x over n. The variance is sum of x minus mu squared over n. This is one of the special cases I was talking about, which, as you can see, it does have nicer, easier ways to find the mean and the variance. And this is the binomial distribution. So everything we've talked about today, even the ones that are not really, we're not really covering, but they're still there in the book, are included. But for future classes, I would leave it up to you. Again, this is just a recommendation. I would leave it up to you to continue to fill out this table every time we cover a new probability distribution. So perhaps in the next class, when I say we're going to talk about a new type of probability distribution called the blah distribution, then you may want to write it down on your table. The blah distribution, write down the PMF, write down the mean, write down the variance whenever we cover it. You don't have to do it, of course, but I would say it is strongly recommended that you do, because when we are looking at the test, it would be a lot easier for you to actually you know, just look up the values straight on a table than to have to go through your notes, say, oh, which day did we cover this? Oh, this was Monday, June 14th, and then have to go back through. I think it's better to have it all in one table. One of my former students did this, and this was a good student, and the former student recommended me this method just for being prepared for the exam. So it's there, it's up to you whether you want to, and it's on D2L at the end of the notes to answer the previous question. And yeah, that basically ends our introduction to probability distribution.